Hello, everyone. Welcome to the talk. Today we're honored to have with us Professor Susan Murphy, who is a professor of statistics as well as a professor of computer science at Harvard University. And she specializes in using statistics in applications to digital health. She has quite a few honors, so including a MacArthur Fellowship, also known as the Genius Grant, and she's a member of the National Academy of Science in America, as well as being a former president of the International Institute of Statistics. Yeah, I hope I got that correctly. It's a huge honor to have you here. Thank you so much.
Okay, so I changed the title a little bit just because I was thinking about this at the moment. And so, as Yuri said, my lab works in digital health. So this involves wearables, as well as smartphones or like Siri. And the whole idea here is that this is a way for us to sense or detect that someone needs help and deliver that help as they go about their life. So if someone is really feeling really anxious, they might get a message about how they could practice deep breathing that they've already learned about. Or if they're feeling really lonely, they might get a connection to some sort of social support. And there's a whole bunch of areas we've worked in, and you can see the little icons for all these different areas, a lot of these areas. The one I'm going to talk about today is HeartSteps. It's a physical activity study. It's really clean, so I can explain things very well. So that's the reason why I'm using it today. So again, how do you use these sensors and these wearables to help us, right? And that's what this is all about. There's sensors on the phone. There's sensors on our wearables. Now there's going to be sensors in our t-shirts, particularly if you're an athlete. Some of these wearables can be used to deliver suggestions, motivation, ideas for what we can do right now to manage different issues, ideas for what to buy at the grocery store if we're trying to manage our weight, stuff like that. So there's two types of interventions that you usually see that are available in digital health. And one is a pull. And this is the kind of thing, if you've ever downloaded an app, you'll see these. There's all kinds of content on the phone, and you can go to the phone and you look at, in particular, I'm talking about a phone. You go to the phone and you see content there. Like it might be, for example, if you're a student at Harvard and you're having a lot of problems in a class, you could go to the phone and see how to contact the academic resource center, or how to contact student groups that work together and study together. That's called a pull. That requires that you recognize you have you need some help right now, and you go and you access that help. The pushes are a little different. Pushes are where using those sensors or how you've been engaging with the app or the phone, the software on the phone detects that this is a time at which you could use some help for a particular issue. And then the phone or the wearable interrupts you and sends you a notification, pings, whatever. And I think most of you have probably downloaded an app, and you know what I mean when I say interrupt and aggravation. I mean, it's a big hassle. The great thing about pushes is you don't have to recognize you need help. So often the very times we need help, that's the times we're least likely to recognize it. So pushes have enormous potential, but they have an enormous downside too. And how do you balance that downside and that upside up together is where the data science comes in. So questions that are really critical when you're thinking about personalization of when to deliver these pushes, in what settings, time of day, how you're feeling. This is all about personalization. So when is it most useful for the digital device? I'll say interrupt you in order to provide help. Should the type of help vary depending on how good the weather is outside, whether or not you're around other people right now, whether it's in the morning, what your mood is. And as you experience this app, should the answers to those two first questions change? Because you have a lot more experience, and the answers might very well change with time. And the way we think about addressing these kinds of questions using data is we combine different scientific domains. And the scientific domains have to do with behavioral. The behavioral domain, this is mainly psychology, a little philosophy, health, medicine, as well as data science. So data science, it's mathematics, applied math, computer science, and statistics, and engineering as well. And I'm on that side, the data science side. So in terms of the application we're going to look at today is HeartSteps, and this is for individuals. So these are for middle-aged individuals, okay? And they're pretty sedentary. And the main goal is to develop an app for people who have hypertension, high blood pressure. And there's 3 studies, and I'm going to talk to you about all of them. First, the blue, the 42-day study, the 6-week study. And I said it's micro-randomized. I have to explain what that means. Okay, so in this first HeartSteps V1, everybody was wearing a band, a tracker, and it measured how active they were in real time. Like every 5 minutes, even shorter intervals, the data would go to the cloud. And we had sleep quality. There was a lot of sensors on the phone. We knew how busy your Google Calendar was, your location, the weather, how much you've been engaged in the app. And we also got some self-report from people, whether or not the app was aggravating them and so on. It's 2 of the big questions. There were a lot of questions, but 2 of the big questions we wanted to address when we were figuring out when to deliver these support to help people be more active is, how might the smartphone help you plan how active you're going to be tomorrow? You do that in the evening, maybe. And in what settings, real-time settings, should the smartphone provide, ping, light up, and have a notification that comes up to give you an activity suggestion that you could use wherever you were with the weather you had at that moment? So what we did was we ran what we call a micro-randomized study. And this is a study that the main purpose of this study, so if you're familiar with how we get drugs on the market, there's these big trials where people are randomized to one of 2 groups and you compare one medication versus another. What we're talking about here is totally different. Here, we're trying to figure out when is the best time to deliver, say, an activity suggestion. Should we deliver it in the morning to some people, in the evening to other people, and so on? And should it depend on what the weather is and how burdened they feel, and so on? So these are called micro-randomized. So it's all about constructing a mobile app. And what happens is, on each individual, every time you might potentially deliver an activity suggestion, you randomize them. That means each individual, and I'll explain what I mean by randomization, each individual is randomized many, hundreds and hundreds of times. Actually, I got to tell you guys, every time you go on the web and you access Google or any of these web interfaces, you're being randomized hundreds and hundreds of times just okay. Anyway, so now we're talking about health though. So in this case, in the case of the activity suggestion, the randomization could happen around 5 times a day. And these were 5 times that the user felt were pretty good. And it was related to morning, midday, and so on. You see the times there on the slide. And the randomization is around 60, like for example, in the morning, with 60% chance, you would get an activity suggestion, and with 40% chance, you wouldn't get any suggestion. And that happened at each of those 5 times every day over the 6 weeks. With the evening planning, that was only at night, you would get randomized once in the evening, and only on about half the days. So you might, on any given day, you might get randomized to plan how you're going to be active tomorrow. Lots of randomizations here. So when we talk about randomization, 5 times a day, and I said 60% chance. So what I mean is that this probability of being getting a message, it's 0.6. This is completely non-systematic. It's as if there were a bowl with 10 white little cards in it, and of which 6 have, say, send, and 4 do not, and you mix it up and you pull one out. So it's not related, this randomness, this randomization is not related to anything going on in that person's life. It's just with 60% completely by chance. 5 times a day, over 42 days. So I wanted to show you some of the screenshots from this. So on the right side, that's the activity suggestions. If you got randomized to an activity suggestion, then you could get one of 2 types. And this is the facing part of the app. So you can see the notification at the top, the one about, so how about, this was while I was at work. How about taking a few minutes to enjoy nature, head outside, walk until you see a wild animal, even if it's just a squirrel. So that's the only wild animal I'm going to see here, actually, besides a rat. But either squirrels or rats. But anyway, it could have either one of those. So this is kind of a, it's a nice little message. This only happens when I'm at work. And it takes me about 3 minutes, maybe. It's a little burdensome. It takes me 3 minutes. The other message, at your desk, so this is happening because I'm at work, wouldn't happen at home. I wouldn't get this message at home. It says, stretch your feet, lift your heels. Everybody loved these messages, made them feel really good, but they don't have to move at all, right? So this takes almost no burden at all. So that's the 2 types of messages you could get. Each one looks totally different from the other, but one takes about 3 minutes of time. The other takes almost no time. The evening planning is very similar. There were 2 types of ways. If you got randomized to evening planning, you would be asked to plan your activity tomorrow. The one on the far left, that's a list of things you've done already in the past. And all you have to do is click the one you want to do tomorrow. That's really nice. You don't have to think much. You just click the one that you like best or you feel like you might like tomorrow. The one that's further, it's still on the left part of the screen, but further to the right, that's an open box. And you have to sit there and type in what you're going to do tomorrow. It's a total hassle. So in both of the activity planning and the activity suggestion, the evening planning, there's 2 options if you get a suggestion or a message. One is a little onerous and one is not onerous at all. That's the key way they differ. So I'm going to focus right now on the activity suggestions. Again, I've already gone through this, 42 days, 5 times a day, around an average of 3 times a day. You'd get it because we were randomizing with probability 0.6. And here's another example of a message I got in the morning. It was pretty cold that day. It's trying to help me get the right framing in my mind. Now, why are we sending these activity suggestions? Well, the idea is that this will motivate the user to get up and move and hopefully get a walk over the next 30 minutes. So that's kind of the goal. And if you don't get a message, you may not walk, but if you get a message, hopefully you'd walk. And there's a lot of other interventions that are going on in these individuals' lives. And the combination of this, the activity suggestions, the planning, and the other interventions, the idea is that combination will produce a longer-term impact on these individuals. Remember, these are sedentary individuals, and you want to give them, help them have ideas for how they can work activity into their lives. And that's the idea. And then over longer, even longer time periods, you want to reduce the chance they're going to get a heart attack or have other heart diseases. But this is all, so this is activity suggestions, just one small part of that whole package. This is how you think. Everything is being built together. Now, a really interesting thing, this happens all the time. If you're going to push messages to someone as they go about their life, then you really don't want to do that. You don't want to interrupt them if it's at a bad time. For example, if the sensors on the phone detected that you were so this is in the States, and most of the time, if someone's moving quickly, they're probably driving a car. So if the sensors on the phone detected that you're moving very quickly, then you might be operating the car. And it's really inappropriate for the phone to try and interrupt you and suggest that you go for a walk. That just doesn't make any sense. So you're not available. You don't even get randomized then. It's just not an option. If the sensors on the phone detect that you're currently walking, you won't get randomized. And why is that? Because all of these messages are about doing something different from what you're doing now. And that's kind of stupid. Someone's already walking and you ping them and suggest they do some other kind of walk. That just doesn't make sense. And also all of these users could turn off the intervention. So like if I had a whole bunch of committee meetings in a row, or like I was giving a talk like right now, I would turn it off so that I wouldn't get interrupted. So, the person always has control. So that's what determines availability. People are not available in any of these three settings, and they only get randomized. They're only considered, we only consider providing a suggestion if they're available. Now you see in blue, I put is walking, and this turns out to be really critical. Because suppose you're in this study, or you have our app called HeartSteps, and you really get engaged with the app. It's really helping you, and you start being active during those 5 periods during the day, the 5 periods I mentioned earlier. Then you're going to probably already be walking. We won't even deliver a message then to you, right? This is important to remember for the next slide. Okay, so let's think about the effect of the activity suggestion, giving an activity suggestion versus not sending a message on the subsequent 30-minute step count. Of course, I want to know if that effect depends on the weather outside, if you're at home or work, time of day, whether or not last night you said that the app was really aggravating you or not, and so on. But let's not go there just yet. Let's just look overall, what is the effect of this activity suggestion versus not getting a suggestion on your step count. So when we were designing this study, I drew that little graph on the bottom right-hand side. The x-axis, the horizontal axis, is the decision times. There's 210 because it's 5 times a day over 42 days. The y-axis, the vertical axis, is like a standardized effect size. It doesn't have a lot of meaning because you don't know the scale here. But the content here is at the beginning of the study, at the decision point 0, probably people are too confused. They won't even notice the notifications. They probably won't have any effects. Thus, the value on the y-axis is around 0 at time 0. But then as time goes on, the value on the y-axis, if you look at the black curve, it gets higher. That's because if I get a message, I walk, but if I don't get a message, I just do my own thing, which means I'm sitting, working, right? Then notice that curve has a downturn later on. This is our biggest concern. Our biggest concern was after a while, the user is going to habituate. I don't know if you guys have ever heard of that word, habituate. This is a thing that occurs in psychology and cognitive science. If you get repeated stimuli over and over again, you eventually don't even see the stimuli. This happens at night, like if you have a train that goes by, after a while you don't even hear the train anymore. So these activity suggestions are like repeated stimuli. So what we might expect if we're not careful, we're giving people them around 3 times a day, that the effectiveness is going to dissipate just because people are going to habituate, or they're going to get aggravated and they'll ignore us. So that's why there's a downturn closer to time 200. There's another reason why this curve might turn down. Remember, you only could get randomized. We'd only discover whether or not you were more responsive if you got a message versus if you didn't get a message, if you're currently available. And people who are currently walking are not available. So at the beginning of the study, near time 0, these are all sedentary people. They're pretty much all available, unless they're driving, and I'll ignore that. They're all available. So the contrast between getting a message versus not includes everyone who's there, all the sedentary people. But as time goes on, some of those people are going to really start to like the app. And they're going to start walking anyway, because they're going to build walking into their life. They're not going to be available anymore. Who is left? Who is getting randomized as the study goes on? The people who are the least reactive, the least responsive to the app. So of course you might expect to get a downturn, because now, closer to the end of the study, the only people that are getting randomized are the people who, for whatever reason, these activity suggestions are not helpful. It's very interesting. Now, in the actual analysis of the study, we didn't see any evidence of that second reason, but it was something that was right in our mind the whole time, that you might get that. And this way of thinking, of seeing a curve and having very different alternative explanations, one of which has to do with the changing composition of people who are experiencing things over time, that's uniquely statistical, and it has its origins in philosophy and the foundations of statistics. So what did we learn when we ran this study? It turns out it was fantastic. The data indicated that individuals were really responsive to these activity suggestions, with an increase. If they didn't get a message, they weren't as active as if they got a message. And it also turns out that most of that effect was due to those 3-minute messages, not the ones that made them feel good because they were rolling their shoulders or rolling their toes or whatever. No, it was the higher burden messages. Unfortunately, the effect deteriorated with time. So it was a 6-week study. By about 3 weeks in, nothing is going on. So let me just recap that. At the beginning of the study, closer to the beginning, people on average increased their steps by around 271 steps in 30 minutes. It turns out for sedentary people, this is about a doubling of how active they would normally be. So this is a massive effect. But by halfway through the study, day 20, 21, it's gone. It's really sad. And so then this is great results. I mean, it's very interesting results, but now we're thinking about the next 2 studies, V2 and V3 of HeartSteps. We're wondering, what should we do? Well, we need to somehow have an algorithm that takes into account the fact that someone is becoming less responsive and backs off. Why do I say that? This goes back to the theory from cognitive neuroscience with habituation. So if you get habituated because you're getting repeated stimuli, the way you dishabituate is you reduce the stimuli. In fact, you stop it. And then what happens is you wait a period of time and you start the stimuli again, and all of a sudden people are responsive again. It's very interesting. So can we have an algorithm that processes data? If these are algorithms from computer science, that backs off when you appear to habituate, allows you to dishabituate, and then comes back. Because the whole goal is to get you to be more physically active over the whole 6 weeks. Okay, so now we're going to the next 2 studies. And in fact, they weren't over 6 weeks. They were over much longer time periods, 30 days, 9 months. And I say they're both personalized because now we have an algorithm doing the micro-randomization. And I'll talk to you about what I mean by personalization here. What does it really mean? Okay, so in a micro-randomized trial, what we saw is that every user, every individual is randomized many, many times, 210 times in the first study. One way you can determine those randomization probabilities is the way we did in the first study. We just set it at 0.6, and we used a software algorithm to send a message with probability 0.6. One could use an artificial intelligence algorithm to choose that randomization probability. And that AI algorithm could use predictions of how burdensome you think that you may be, how burdensome or how habituated you are. And this all involves what's called reinforcement learning. So reinforcement learning is an area of computer science. I'm sure most of you have heard of machine learning, and there's 3 areas of machine learning: supervised machine learning, unsupervised machine learning, and reinforcement learning. Reinforcement learning has to do with sequential decisions as to when to send the messages and what kind of message. And the idea is reinforcement learning personalizes as it experiments with you, with the user. So I have to explain what I mean by that. So what does it mean, personalization? It means that if so far you're more responsive to a particular type of message in a particular setting, then with higher chance, you'll get the message in that setting. You'll get that message in that setting in future. And if you're less responsive, it backs off and you're less likely to get that kind of message. So that's what it means by personalization. It means that if you're not being responsive to a particular kind of message, we don't bother you that much with that message. Whereas if you are, you might get that message more frequently, that type of message more frequently. Should I stop now and ask if there's a question?
Yes, if anyone has any questions, please do ask.
I'll fix my screen.
Yes. Actually, one thing can I ask? So this relies quite a lot on your phone detecting what you're currently doing, where you are, and so on. Is this actually accurate? Does this part work well enough?
Right. So it works like a good fraction of the time, but it doesn't work like, I don't know, 10% of the time or so. It depends on where you are, okay? How highly networked your community is. And so we have to always, when you do the software development, the engineering, you have to plan for all the edge cases. So for example, if we don't know how active you've been recently, what are we going to do? So there's a whole protocol, and that all has to be laid out and made public so that people know. So your instincts are right on. Or like if you're in the basement of some big building, there's no way, we have no way to access,
Thank you.
Stuff. So
someone was asking a question, but I
Yeah,
lost.
please do ask.
do you see there might be an ethical issue where you sort of
So you mean because of the sensor data? I suspect that's what he means, he or she. So what happens is we don't send, for example, we know your location. I mean, the location is sensed, but then we encode it into home, work, or other. And that's all that we have. So when the data set gets formed, the data that goes to the cloud, it just says home, work, or other. So if someone gets access to that, they have no idea where home is. They have no idea where work is. They just see that this person, they don't even know who the person is. They just see home, work, or other at this time. So that protects you. And of course, there's all kinds of rules. I know they are in the UK as well, about how you encode this data as it journeys from the phone to the cloud. And in addition, people have to say, I'm willing to allow my data to be encoded and sent to the cloud for processing. But the critical thing here is that you extract features of the data that are then sent to the cloud as opposed to the raw data. Now, that's what we did in this setting. In other settings, in other studies, it's not that way. And you have to be really careful when you explain that to the person when they join up or they sign up for the app, that they know that, for example, their GPS trace is being sent to a location. And that's much more invasive. But in this study, that was not the case. Okay, so in these V2 and V3 HeartSteps, we actually had multiple algorithms going on, but I'm just going to talk to you about the reinforcement learning algorithm. And the whole game, like I've been saying, is to personalize while we're sequentially experimenting. So, and personalization means the probability, whatever kind of message you're responding to best is the kind of message you're most likely to get in that particular context. And again, you're still interested is when should you send activity suggestions, and when should you, and even more importantly, when should you not bother this person, not send activity suggestions. So it's just a recap. Yeah.
Yeah. Sorry to interrupt. There's just 2 more questions in the chat. But might be asking now. Or yeah. So the first one, it says might be slightly preemptive. So if it is, then we don't answer it yet. But how do you deal with the exploration and exploitation problem in reinforcement learning? And
yeah, this is a big issue, and I'll tell you short. Actually, because you brought it up, I'll make some statements about that.
Yeah, thank you. And then the second one says, so I'm not familiar with how reinforcement learning works, but is it possible to, is it possible to do a local implementation of the AI? And it says, how good is the scaling? I'm not quite sure what this last bit means. If you want to elaborate, please feel free.
So you can, in some studies, we've done local implementations of the whole algorithm. Like we have a smoking cessation study where everything's local. The problem is it puts a lot of burden on the person's phone. And sometimes it can interfere with their use of the phone. So our preference is actually not to do it. Not to, we still have algorithms on the phone, but we try and make them as light as possible so as to not interfere with the performance of the person's phone. Okay, and then the scaling issue is really big. Now here, this algorithm is going to run separately on each individual. And so we're only in the hundreds. I'm not as really worried about this because Google right now and Microsoft, they're doing hundreds and hundreds of thousands. Of course, it's all for ads, which is a little different. But it is an issue. The scaling is really an issue. It's particularly an issue if you start to pull data over users in real time. And we do have some work on that, and it's a big problem for us, is how do you scale? And we use parallel processing. And that makes it even more important to put it on the cloud. Because of course, if you have to pull over users, it can't be on the user's phone, or only a subset of the computations can go on the user's phone. Okay, so this is just a recap. We all know this whole slide. This slide was up here just to make sure we remember what's the activity suggestion. It's whether or not to send, so it's just binary, send versus not. And 5 times a day, 30-minute step count is what we're trying to improve. So one of the big challenges in this area, and I've already mentioned it, is that these suggestions probably in that moment, probably won't have a negative effect. If anything, you'll act on the suggestion and you'll walk. And if you don't act on it, it won't change your behavior. The problem is delayed effects of the actions, delayed effects of the activity suggestions, that is. And that's via habituation, too many stimuli, and burden. You're aggravated because it keeps interrupting you. So this means that whenever you do reinforcement learning, you have to pay attention to this, that you may move the user to a state in which they're even less receptive to your suggestions, either because of habituation or burden. Okay, so now I'm going to talk about reinforcement learning. This is how I talk about it to my colleagues in the domain sciences, like in health. And actually, it really helped. A lot of them have some understanding of applied statistics. So I talk about it from an applied statistics point of view. So every reinforcement learning algorithm is actually 2 algorithms. I'm talking about online reinforcement learning, real-time reinforcement learning. It has 2 algorithms. The first algorithm is a learning algorithm. And a learning algorithm is just it's some sort of modeling, a statistical model. And in particular, we're going to use a Bayesian statistical model if you've had any Bayesian statistics. And this is a model of the user's world, like a model of how their step count might change as a result of getting a message in a particular setting, in the morning, when the weather's good, and so on. It's a model of that. And this Bayesian analysis allows us to update that model in the case of HeartSteps, every night we update that model for that user. That's the learning algorithm. That's just a model. That doesn't tell. And then the second part of the RL algorithm is an experimentation strategy. The experimentation strategy tells us how to randomize whether or not they should get an activity suggestion at that time in that setting: morning, home, work, good weather, bad weather, and so on. And what it does is it uses the experimentation strategy. This is a Bayesian analysis from the learning algorithm. It calculates posterior probabilities. So posterior probabilities are probabilities that are updated after you have received data. So these probabilities are updated and they're based on how responsive that user has been. And we calculate the posterior probability that there's going to be a treatment effect in the state you're in right now, plus a prediction of whether or not there's going to be a negative impact of sending you a message in the state you're in right now. We get that too, and we get that combination. We ask, what is the posterior probability, given everything we've seen on you up to now? What's the posterior probability that the treatment effect plus the delayed effect is going to be greater than 0? If it's going to be greater than 0, that's good. That means, more likely to send a message. If it's less than 0, we're definitely less likely to send a message. So we actually calculate that probability. And that's the probability we use to randomize. So here's where exploration and exploitation in the words of RL are going on. Exploitation is that the probabilities are biased towards, if that posterior probability, the probability that the treatment effect plus the delayed effect is greater than 0 is high, then with higher probability, you get it. That's an exploitation. But it's still a probability. It's not a probability 1. It's a probability less than 1. And that's the exploration. And this is known as posterior sampling in the field of RL. There's some beautiful work on posterior sampling by Ben Van Roy at Stanford. And it has a long history in the reinforcement learning community. And it's this idea of using these Bayesian posterior probabilities that have been updated by inputting data they've already gotten from you to update what's the chance of you being responsive in the next state, in the state you're in right now, actually. It's not the optimal way to do this. It's not the optimal way to balance exploration, exploitation. Exploration is about learning so that you make good decisions in the future. Exploitation is trying to make the best decision you can right now. It's not the optimal way to do this. The optimal way would be to use a dynamic programming argument. The problem is the state space is too high, and these are what's called NP-hard problems. They're problems that you can't solve them. They're not solvable except in toy settings. So the whole game in RL is to produce good approximations to that trade-off. So here's one individual in the study. The vertical axis is the predicted effect of the activity suggestion, and you see the dots. Those are the predicted. And the scale here is not meaningful except for if it's greater than 0, that means we think, the algorithm is saying you're probably going to be responsive if you get a message. The horizontal axis is the time point. So this went in on last summer and last fall. And you see this individual, they start off, they're not very responsive in June 26. And then all of a sudden they get very responsive to getting a message, really high. And then something happens, they become less responsive. But they still stay pretty responsive. I mean, this line is staying above 0. It's looking pretty good. And there's There's 3 arrows, blue, green, and purple, and they're all times at which this user is the least responsive. They're predicted to be these are predictions, so they're predicted to be least responsive. What happens to the randomization probabilities? So the randomization probabilities, when everything is going just great, I don't think can you see my arrow? If you can see my arrow, yeah. So when everything's going great, we allow the randomization probability to be 80% of the time you get a message. But when things start to go bad, the probabilities decrease. And that's due to this. And in fact, we're also including a delayed effect correction in here. When we ran this and we saw this result, this is last summer into last fall, we realized we had made a big mess. Why do I say that? Look at the size of these probabilities. This is the chance of sending an A. This is a time when that user, remember, that user is not very responsive. This is a blue arrow. We're sending that message with about probability 0.55. That's way too high. We realized we had really messed this up. And so we actually had to change the posterior sampling algorithm. And it got changed around this dotted line. So that's why I always put it here. So the next 2 users are all after that period. So here's another individual. This individual started in November of last year and went through the summer of this year. So in August was the last time. That's on the horizontal axis. And there's a dot, all the dots, the heights of the dots are the predicted effect of sending a message versus not. So, positive is good, negative is not good. And they're colored. They're colored about whether or not that user had been going into the app and looking at how good their activity was. That's if they're engaged. Engaged equals true means they've been looking at the app. Engaged equals false means they haven't been looking at the app. Notice the blue dots are all much higher than the red dots. So this is someone who, if you're going to bother them, you should bother them more frequently when they're engaged. That's when they're most likely to take advantage of it. And that's what the algorithm started to do. So here's the randomization probabilities. So now here, the lowest probability is 0.1, no more 0.5 business. We fixed that mess. And so here you see all the blue dots are much higher, the blue probabilities, because the height of the axis, the y-axis is all the probability. They're much higher in general than the red dots. Let's go back one slide. Notice here, even when the person wasn't engaged, they were still sort of responsive at the beginning. This is in early December. So they still were getting messages with high frequency, but then they stopped being responsive and when they weren't engaged. And that's when they got randomized with probably 0.2. That's this lower bar here. Why do you think we didn't allow the randomization probability to go to 0? Any ideas?
Because then you completely lose the exploration part.
Exactly. Then if the user changes their behavior, we're dead. We'll never discover it. And indeed, this user started becoming responsive again in July. And the probabilities start going back up. It's very interesting. COVID is around mid-March. So how does it look around COVID time? This is mid-March. Notice how everything is kind of suppressed. It's very interesting. Okay, I don't know. Let me look at the time. So here's another individual, similar sort of thing. Engaged is blue, red is not engaged. And here was very surprising. See the circles that have a black circle around them? These are times, at that time, in that context, that individual had not been very active over the past week during that time window. And indeed, we're seeing almost no predicted effect of the activity suggestion in that time. So if they generally were not active in that time window, no use sending a message. And the probabilities reflect all of this. You know, I'll just move on with that. But it's very interesting. So looking at the probabilities tells you the personalization in a sense. Okay, so what's our goal here? The long-term goal, like what is my dream? You know, what do I want to do in my life? My goal is that we'll have an app that's continually learning. So it's one of many different types of components on the app, on your phone, and it's continually trying to figure out what's best for you. It'll back off when you get aggravated, when it's no longer helpful. It'll come in when you need help. That's my goal is to have that kind of thing. And that this is via RL, which is this area of computer science. And what does this imply? This implies continual experimentation. And I'm sure some of you realize that this is incredibly contentious idea. People often don't like to know that they're continually being experimented on. But the only way we learn, the only way we can personalize is to continually experiment. Indeed, if I think about, so this has this long history. Continual experimentation goes way back. Fisher is a British person who founded most of genetics in modern day genetics, as well as statistics. And he advocated this iterative nature of experimentation, as well as his protege, George Box. Google and Facebook, I have some quotes here. Of course, this is about advertising, where they place the ads on your website, your email, and so on. They're constantly experimenting. We need to constantly experiment in health to help people help themselves. Okay, so I have one last slide. Okay, let's see if I can do this. I don't know if you guys hear this.
Experiment. Make it your motto day and night. Experiment. And it will lead you
to the light.
The apple on the top of the tree is never too high to achieve. So take an example from Eve. Experiment.
So that's what we got to do. That's it. Thank you.
Yeah, thanks a lot for a very interesting talk. Yeah, thank you. Yes, let's do some more questions. If anyone has any questions, ask away. And
Yeah.
I'll be thinking of questions, I'll ask mine first. So it seems like a constraint, like a big constraint on the app is that all of the activity suggestions, you have to come up with them sometime at the start, and there's only a very finite number of them. Or can the app come up with its own suggestions what to do?
Yeah, so you also want to have continual experimentation, say like with MTurk, on the side where you're generating new messages. So the way our messages here were generated was through a series of experiments on MTurk. First, we would tell people about this person, what kind of and the setting they were in, what kind of messages would they send. Then we had another group of MTurkers rate the messages for usefulness. Then we had another set of MTurkers. So it's a series of experiments, and that pretty much has to go on continuously if you're going to do a roll, you're going to implement it. You have to have some plan for constantly refreshing, because even the way you phrase the sentence changes, right? Mm-hmm. This is particularly a problem. We have a number of studies with adolescents, and there it's even worse. I mean, how fast you have to change things. Like 6 months and all the memes are no longer popular that you thought were popular.
Yeah, thank you. That makes a lot of sense. Here's a question from the chat. Just says, yeah, thank you for the talk. And how effective is combating habituation by changing the type of stimulus?
Yeah, that's another way, you know, there's the idea of backing off, and the other way is to change the type of stimulus. The question is, does the user perceive it as really different? So for example, in HeartSteps, we had those two types, one which was more about just rolling your neck or rolling your shoulders, and the other was actually more burdensome, take a 3 to 5 minute walk. And we didn't really see, I don't think, I mean, the individuals, they liked the easy suggestion more than the more burdensome suggestion, but the habituation still occurred. So that's a critical fine point, is, does the individual perceive the stimulus as really different or not? And that's hard. I think it's something that has to be dealt with eventually. It's a great question.
Okay, yeah, thank you. Yeah, so if anyone else has any questions, please ask. Yeah.
Actually, so speaking of the activity suggestions, the less onerous suggestions like stretch your legs, stretch your shoulders, does make no effect, right? Because we don't know if they really do this when we suggest them to do this. We only know if they go to a walk or not.
Yeah, so before this study was run, there was all these two-arm trials where, so two-arm means two groups of people. One group got the app, one group didn't. And the group that got the app would get similar messages like just roll your shoulders or stretch your feet. And that group actually looked like it was doing better than the group that didn't get messages. And the idea was, once you start to stretch your feet, you become aware that you're tired of sitting and you get up and move. We didn't see any evidence of that. But that was the idea that people had thought, and that was the rationale for this. They thought, if they get you just to be sort of aware in a very low burn way, all of a sudden you'll get up and move. It didn't work out. So now in the future, in the HeartSteps V2 and V3, we're actually getting heart rate. And we only randomize people to these kind of messages when they're sedentary, like they're working at their desk. And we look to see, does their heart rate increase or not? Because when you stand up, your heart rate increases. So, because we gave up on it being a way to get you to go walk. That didn't work out for us.
Thank you.
Any other questions?
Hello. So I have a question. Thank you for the very interesting talk, first of all. So my question is, so you've got all of these different RL agents which you're training on different people, but is it possible to sort of transfer some of the knowledge that knowledge is a fairly weird term to use here, but some of the sort of knowledge that one RL agent sort of gains to another RL agent? Or is it possible to like make changes as you go along, if you know what I mean?
No, I think that is the way we have to go in the future. So what'll have to happen in the future, because this is very noisy settings. And so we really want to use data from people like you to help us figure out what to do for you. I think this is what you're asking. Is that correct? Or?
Yes, and also how would you like do it from like more of like the statistical and mathematical point of view too?
Right.
Sorry. Yes. Thank you.
So there's a whole variety. If you're familiar with CRL and multitask learning, there's a whole variety of ways that people do this. But okay, so I'm taking a classical statistical approach, and so we actually did add people to this study. And we are doing this kind of pooling of data on the cloud in order to randomize, to personalize for each person. And what we did was we used random effects models, which is a classical kind of model in the health field for determining how much to pool information across individuals. It turns out that's a way to structure the Gaussian process kernel. So it fits in to Gaussian process learning, which is a Bayesian learning method. So it sort of fits into what the CS people were already thinking of, but it's a much more structured way. But this is definitely like multitask. Oh, and we're using Bayesian methods. Our priors are informative. So prior data is used to build our priors. We don't use non-informative priors or flat priors. We don't do any of that kind of stuff. Yeah.
Thank you.
Yeah.
Here's another question in the chat. So how should the algorithm change if the reminder is for something where habituation is more dangerous, e.g. for taking an important pill? So would the lower bounds for the suggestion probabilities be higher, for example?
Yeah, that's a good question. We do have a study. This is with adolescents and young adults who had leukemia, and they have now to do 3 years of take-home chemotherapy once a day. Take a pill once a day. These pills are not nice, okay? There's a lot of side effects, but if they don't take that pill, I think more than 80% of the days, their chance of getting leukemia again is very high, and they'll likely die. So it's really critical that they take that pill every day. And we're supposed to, right now we're just micro-randomizing. We're not, there's no AI algorithm going on. The problem is if we send you a reminder too many times, you won't see it anymore. So normally what happens is you have multiple, what we call intervention components. So like on this screen, there's 2 intervention components. There's the planning the night before and the activity suggestions. So in that setting, there'll be multiple ways that we try to help you remember. And in this particular case, all of these adolescents, their parents also have an app that we do that. So both the adolescent and the parent has an app. They're slightly different, but so we're trying, so there's multiple ways that we try and encourage adherence, but we can't just send a reminder every day. I mean, we can, but it's not gonna make any difference after a while. This goes back to one of the first questions someone asked me, could we change the content of the reminder in some way to reduce habituation? This would be an important place for that. Then maybe we could send a reminder every day if we could make the content so different that it would be perceived as very different.
Okay, your last call for any questions. Anyone else? So yeah, if there aren't any more questions, yeah, let's all thank Professor Murphy once again. It was a really interesting talk, and it's great to see statistics being used for the greater good rather than just for advertising. Yeah. Yes, best of luck with the app. It'll hopefully it works really well. That'll be quite exciting.
Yeah, thanks for spending the time with me.
Yeah, thanks a lot.